Look up at the night sky, and what do you see? A vast expanse of stars, galaxies, and darkness stretching farther than our eyes can comprehend. But here's the thing, what we're seeing is just a tiny fraction of reality. Our observable universe, as enormous as it seems, might only be a speck in something far grander, something beyond the limits of our telescopes and even our wildest imaginations. What if our entire cosmos is just a single bubble floating in an infinite cosmic ocean? What if there are other universes out there, each with its own laws of physics, its own versions of time and space? The truth is, we don't know, and that's where the mystery becomes thrilling. For centuries, humans have pushed the boundaries of understanding, from Galileo's telescope to the Hubble Space Telescope, each revealing layers of the cosmos we never knew existed. But beyond the edge of our observable universe, beyond the farthest galaxies we can detect, lies a frontier that defies even our most advanced science. Is there an endless multiverse with realities stranger than fiction? Could our universe be one page in an infinite cosmic library? These aren't just sci-fi ideas, they're real theories explored by physicists, cosmologists, and philosophers trying to answer the ultimate question: what lies beyond? Today, we're diving into 25 of the most mind-bending theories about what might exist past the boundaries of our known universe. Some sound like something from a dream, others could rewrite everything we think we know about reality. From cosmic bubbles to hidden dimensions, from parallel worlds to the idea that we might be living inside a simulation, each theory opens a door to possibilities that'll leave you questioning everything. So sit back, let your curiosity take over, and get ready to explore the greatest unsolved mystery of all, the unknown that lies beyond our universe. This journey is about to get fascinating. The first theory takes us into the realm of the multiverse, the idea that our universe isn't alone, but just one of countless others, each with its own unique set of rules. Think of it like a cosmic patchwork quilt, where every stitch represents a different universe, some eerily similar to ours, others wildly different. What if, in one of those universes, gravity is twice as strong, or time runs backward? Or what if the very laws of physics we take for granted don't even exist there? This isn't just a wild thought experiment, it's a serious scientific possibility backed by quantum mechanics and string theory. Take quantum mechanics, for example. When particles interact, every possible outcome branches off into its own separate reality. That means every decision you've ever made or didn't make could be playing out in parallel worlds right now. Then there's string theory, which suggests that our universe might float in a higher dimensional space, like a soap bubble in a sea of other bubbles. Some universes might collide, others drift apart forever, each one a self-contained cosmos with its own story. One of the most fascinating voices in this field is physicist Max Tegmark, who broke down the multiverse into 4 distinct levels. The first level, universes so far away that light from them hasn't reached us yet, essentially distant copies of our own reality. The second introduces universes with different physical constants, places where atoms might not even form. The third dives into quantum branching, where every possible outcome creates a new timeline. And the fourth, that's where things get truly bizarre, universes governed by entirely different mathematical laws, realities so alien we can't even begin to imagine them. So the next time you look up at the stars, ask yourself, what if our universe is just one tiny chapter in an infinite cosmic library, each book telling a completely different story? Now imagine an endless cosmic ocean frothing with bubbles, not soap bubbles but entire universes, each one a self-contained reality floating in something far grander. This is the bubble universe theory, where our cosmos might just be one delicate sphere in an infinite sea of others. The idea stems from inflation theory, which suggests that in the earliest moments after the Big Bang, space itself expanded faster than light, stretching the fabric of reality like a balloon inflating to unimaginable sizes. But here's the twist. What if that inflation never really stopped? What if it's still happening right now, far beyond the edges of what we can see, birthing new universes like bubbles in a boiling pot? In this scenario, each bubble universe forms with its own unique physics. Some might have stronger gravity, others might be filled with exotic particles we've never encountered. And just like soap bubbles, they can collide cosmic crashes that could leave scars on the sky. Scientists have even searched for these scars in the cosmic microwave background, the afterglow of the Big Bang. Picture it like finding a fingerprint on a window, a faint circular pattern in the radiation that blankets our universe, hinting at a long-ago collision with another reality. The wild part, some of these bubbles might be entirely alien to us, with different dimensions or forces we can't even comprehend. Others could be nearly identical with slight tweaks, like a universe where electrons are just a fraction heavier, making life as we know it impossible. And if inflation is truly eternal, as some theories suggest, then the number of bubble universes could be limitless, an ever-growing cosmic foam where new realities are born every instant. So the next time you hear about the Big Bang, remember, it might not have been the only one. Our universe could be just one bubble in an endless cosmic ferment, a single note in a symphony of realities we're only beginning to imagine. What if everything you see, touch, and experience, every star, every galaxy, even your own thoughts, is nothing more than an illusion? That's the mind-bending premise of the holographic universe theory, which suggests our three-dimensional reality might actually be a projection from a two-dimensional surface at the edge of the cosmos. Picture a movie screen. The images appear lifelike with depth and movement, but in reality, they're just flat patterns of light. Now imagine that on a cosmic scale, our entire universe as a flickering hologram, with the true source code of reality encoded on a distant two-dimensional boundary we can't even perceive. This idea didn't come from science fiction. It emerged from the study of black holes, those cosmic enigmas where gravity is so intense that not even light can escape. When physicists like Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder, it raised a paradox. How could something swallowing everything, even information, have measurable properties? The answer came when researchers realized the information swallowed by a black hole might not disappear but could be encoded on its event horizon, the point of no return. Think of it like a cosmic hard drive storing data in tiny, two-dimensional pixels. From there, the leap to the holographic principle was astonishing but logical. If a black hole's information is preserved on its surface, could the same be true for the entire universe? Some physicists argue that all the information making up our 3D reality, every particle, every force, could be painted on a distant two-dimensional boundary like a shadow cast by a flickering flame. The implications are staggering. It would mean that space itself, the very fabric we move through, is an illusion, a projected depth that doesn't fundamentally exist. Even stranger, this could solve one of physics' biggest headaches, uniting quantum mechanics with gravity. In a holographic universe, gravity might not be a fundamental force but a side effect of how information is encoded and projected. Experiments are already testing this, like the GEO 600 gravitational wave detector, which in 2008 detected unexpected noise that some scientists believe could be quantum foam. Tiny fluctuations hinting at reality's pixelated nature. So the next time you reach out to touch something, ask yourself, are you really feeling solid matter or just the echoes of information flickering from the edge of existence? What if the Big Bang wasn't the beginning, just another chapter in an endless cosmic loop? The cyclic model rewrites the story of our universe, suggesting that instead of a single explosive birth, reality is caught in an infinite dance of expansion and collapse. Picture a cosmic heartbeat. The universe expands, galaxies drift apart, and then eventually gravity pulls everything back together in a cataclysmic big crunch. But instead of ending there, that collapse becomes the spark for a new Big Bang, birthing a fresh universe from the ashes of the old one. This isn't destruction, it's rebirth on the grandest scale imaginable. One of the most compelling aspects of this theory is how it sidesteps the singularity problem, that mysterious point of infinite density where our current physics breaks down. In the cyclic model, the Big Bang isn't a true beginning but a transition, like turning the page in a book. The universe contracts to an incredibly dense state, but not infinitely so, allowing the laws of physics to hold firm. Then, like a coiled spring, it rebounds into a new expansion phase. Some versions of the theory even suggest that each cycle remembers traces of the last, like echoes in space-time that could subtly shape the next universe's structure. How would we even detect evidence of these past cycles? Theorists propose that gravitational waves, ripples in the fabric of space-time, might carry imprints from previous universes, like faint whispers from a time before time. Or perhaps the cosmic microwave background, that ancient afterglow of the Big Bang, hides subtle patterns or anomalies that point to an earlier cycle. Even the distribution of galaxies across the sky could hold clues, like cosmic fossils buried in the structure of reality. The implications are staggering. If the cyclic model is true, our universe isn't just one story, it's a single volume in an endless library, each iteration written with slight variations. Maybe in the last cycle, stars burned brighter or dark energy behaved differently. Maybe the next universe will inherit some hidden signature of our own, a cosmic fingerprint waiting to be decoded. It's a vision of eternity that turns the idea of a beginning and end on its head, replacing it with something far more profound. An infinite symphony of universes, each one rising, falling, and rising again. Imagine standing at the edge of time, watching as the universe contracts around you, not with fear but with awe, knowing that this isn't the end. It's just the universe taking a deep breath before the next great expansion begins. Imagine a sheet of paper suspended in midair, a flat, two-dimensional world where its inhabitants can only move forward, backward, left, or right. Now picture our universe as something similar, but with an extra dimension, a three-dimensional brane floating in a space with more dimensions than we can perceive. This is the brane world scenario, a radical idea born from string theory that reshapes our understanding of reality itself. String theory proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. But for this math to work, those strings need more room to vibrate, not just the 3 spatial dimensions we know, but as many as 10 or 11 in total. So where are these extra dimensions? The brane world theory suggests they're all around us, folded up so tightly we don't notice them. Like the way a garden hose looks like a line from far away but reveals its true cylindrical shape up close. Our universe, then, might be a 3-dimensional brane embedded in this higher dimensional bulk, like a slice of bread in an unseen cosmic loaf. And here's where it gets wild. Other branes could be floating out there too, parallel to ours, each its own separate universe. Some might be empty, barren landscapes. Others could harbor alien forms of matter or even alternate versions of us. Every so often, these branes might collide, cosmic earthquakes shaking the fabric of reality. Some scientists think such a collision could have triggered our own Big Bang, like 2 sheets of paper smashing together and igniting a firestorm of creation. The echoes of these collisions might still be detectable. Ripples in the cosmic microwave background, subtle temperature variations in the ancient light bathing our universe could be the scars of a long-ago brane crash. Even gravity, the weakest of the fundamental forces, might be leaking into our brain from another, explaining why it's so much feebler than the other forces. Picture standing in a dark room, sensing something moving just beyond your vision. the brane world scenario hints that reality as we know it might be just as limited, a thin slice of existence in a far vaster, stranger cosmos we're only beginning to glimpse. What if the universe isn't real, not in the philosophical sense, but literally a meticulously crafted simulation, an artificial reality running on some hyper-advanced civilization's cosmic supercomputer? This is the simulation hypothesis, a theory that sounds like science fiction but has gained surprising traction among philosophers, tech billionaires, and even some physicists. At its core, it suggests that everything we experience, the stars, the oceans, even our own consciousness, might just be lines of code in an unfathomably complex digital construct. The idea isn't entirely new. Philosopher Nick Bostrom formalized it in 2003 with his now famous trilemma, which breaks down to three stark possibilities. Either nearly all civilizations like ours go extinct before reaching technological maturity, or advanced civilizations lose interest in creating simulations of their ancestors, or here's the kicker, we're almost certainly living in one of those simulations right now. Why? Because if even one advanced society ever runs ancestor simulations, they could create countless virtual worlds, making simulated minds vastly outnumber biological ones. Statistically, the odds tilt heavily toward us being in the simulation, but how would we even know? Some theorists suggest looking for glitches, tiny imperfections in reality that could hint at underlying code. Think of it like spotting pixelation in a video game. For instance, quantum mechanics already shows particles behaving strangely, existing in multiple states until observed. Could that be a processing quirk, the universe optimizing resources by only rendering details when needed? Or take the speed of light, a cosmic frame rate limit preventing the simulation from overloading? Even déjà vu has been joked about as a memory buffer hiccup. Silicon Valley has taken the idea seriously, with figures like Elon Musk openly speculating about our odds of living in base reality. Meanwhile, physicists have proposed experiments to test the hypothesis, like hunting for patterns in cosmic rays that might reveal a pixelated structure to space-time, or searching for mathematical anomalies in the fundamental constants of nature. But here's the twist: if we ever proved we're in a simulation, what then? Do we try to communicate with the creators or risk triggering a shutdown? Or does the discovery itself become part of the simulation's design? The questions spiral endlessly, blurring the line between science and metaphysics. So the next time your phone glitches or you notice something oddly coincidental, ask yourself, is this just reality, or is someone or something running the code? Black holes are cosmic vacuum cleaners, swallowing everything that crosses their event horizon. But what if the universe has a way of spitting things back out? That's the essence of the white hole hypothesis, a mind-bending twist on Einstein's theory of relativity. While black holes pull matter in past the point of no return, white holes would be their cosmic opposites, regions of space-time where nothing can enter, only explode outward in a torrent of energy and matter. Picture a black hole running in reverse, a cosmic geyser erupting with the stuff of creation instead of devouring it. Now here's where it gets truly wild. Some theorists suggest our entire universe could be the aftermath of a white hole's eruption, a big bounce from another reality's collapse. Imagine a supermassive black hole in a parent universe, crunching down to infinite density before rebounding as a white hole, birthing our cosmos in the process. This wouldn't just explain the Big Bang, it would imply our universe is connected to another through a sort of cosmic umbilical cord, a wormhole threading through the fabric of space-time itself. The math is surprisingly plausible. Einstein's equations allow for white holes just as they do black holes, though we've never observed one. They'd violate the second law of thermodynamics by spewing out order from nowhere unless, of course, that order came from another universe's destruction. Quantum gravity models even suggest that when a black hole's evaporation finishes via Hawking radiation, it could transition into a white hole, recycling its stored information in a fiery rebirth. What would evidence for this look like? Astronomers have scoured the sky for unexplained high-energy explosions, brief, intense bursts of radiation with no visible source. Some speculate these could be white holes briefly flickering into existence before collapsing under their own instability. Others hunt for subtle imprints in the cosmic microwave background, patterns that might reveal our universe's birth as an eruption from something older. This theory blurs the line between death and creation. If true, every black hole in our universe might someday become a white hole in another, each collapse seeding a new reality. Our entire cosmos could be one link in an endless chain, with universes giving birth to universes through wormholes we'll never see but can dare to imagine. Picture a universe that never stops growing, not just expanding at the edges, but sprouting entirely new universes like branches from an endless cosmic tree. That's the heart of eternal inflation, a theory that reimagines the Big Bang not as a one-time event, but as a seed for infinite creations. Here's how it works. In the earliest moments after the Big Bang, space underwent a period of hyper-fast expansion called inflation. But what if that expansion never truly ended? What if, in some regions, it slowed down to form stable universes like ours, while in others, it kept raging on, birthing new cosmic bubbles with every passing instant? This idea hinges on something called a false vacuum, a precarious state where space is teeming with latent energy, like a stretched rubber band waiting to snap. Quantum fluctuations, tiny, unpredictable shifts in energy, can cause pockets of this false vacuum to decay into stable states, releasing their pent-up energy in bursts that ignite new universes. Each decay creates a pocket where inflation stops, allowing matter and physics to take hold. But outside these pockets, the false vacuum keeps expanding, endlessly spawning more bubbles. The result, a multiverse where every possible variation of physical laws plays out somewhere in the froth of space-time. Some of these pocket universes might look eerily familiar, almost like ours, but with slight tweaks. Maybe gravity is a fraction weaker, or dark energy behaves differently. Others could be utterly alien, with forces and particles we've never imagined. The terrifying beauty of eternal inflation is that it doesn't just allow for different physics, it demands them. Every possible combination gets its own universe, a cosmic lottery where the winners are the realities stable enough to form galaxies, stars, and life. The evidence for this might be written in the sky. If our universe collided with another bubble in the distant past, the crash could have left scars in the cosmic microwave background. Subtle temperature variations shaped like concentric circles, like ripples from a pebble tossed into a pond. Scientists have searched for these signatures, though none have been confirmed yet. Even more mind-bending is the idea that new bubbles could be forming right now, beyond our observable horizon, their edges rushing away from us faster than light can travel. In an eternally inflating cosmos, the Big Bang wasn't the beginning. It was just our local moment of creation. Beyond our cosmic bubble, the false vacuum keeps churning, spawning universes without end. It's a vision of reality where beginnings and endings lose meaning, replaced by an infinite crescendo of cosmic births, each one a new experiment in the laws of physics. Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity crushes matter into oblivion. But what if these destructive behemoths are also creators? The black hole cosmology theory flips everything we know on its head, suggesting our entire universe might not just come from a black hole, but could actually be inside one right now. Imagine a Russian nesting doll of realities, where each black hole in a parent universe births a new cosmos within its depths, complete with its own laws of physics and even its own black holes, spawning universes ad infinitum. This startling idea stems from a strange symmetry in Einstein's equations. When matter collapses into a black hole, it doesn't just vanish, it reaches a point of infinite density known as a singularity. But singularities break physics as we know them, suggesting something weirder might be happening. Some theorists propose that instead of collapsing endlessly, the singularity bounces, erupting into an entirely new space-time fabric, a baby universe. Our Big Bang, then, could have been the explosive rebirth of matter and energy squeezed through a black hole's crushing grip in another reality. Here's where it gets even more fascinating. This model might explain dark energy, the mysterious force accelerating the universe's expansion. If we're inside a black hole, the energy driving that expansion could be the remnant pull of the parent universe's gravity, subtly stretching our cosmos from the outside like an invisible hand. It's as if the very fabric of our reality is still feeling the echoes of its violent birth. Evidence for this theory could lie in the cosmic microwave background. Some researchers suggest tiny anomalies in this ancient radiation patterns or asymmetries might reveal the shape of our universe's black hole origins. Others speculate that the distribution of galaxies could hold clues, their large-scale structures mirroring the turbulent forces at work during our universe's formation. But the most mind-bending implication, if every black hole births a new universe, then the black holes in our cosmos, like the one at the center of the Milky Way, might themselves be cosmic wombs, each harboring an entirely new reality within their inky depths. We could be living in a black hole's legacy, part of an infinite chain of universes nesting within universes, each one a testament to gravity's power not just to destroy but to create. So the next time you gaze at the night sky, consider this. The darkness between the stars might not be empty at all, but the walls of an unfathomably vast cosmic chamber, with our entire existence unfolding inside the belly of a beast from another world. What if there's a version of reality where everything is flipped, left becomes right, up becomes down, even time itself flows backward? This is the mirror universe theory, a spine-tingling idea that suggests our cosmos might have a perfect opposite, a parallel realm where the laws of physics aren't just different but inverted. At first glance, it sounds like pure science fiction until you dig into the strange symmetries woven into the fabric of reality itself. The foundation of this idea lies in something called CPT symmetry, a cornerstone of modern physics. CPT stands for charge parity and time, three fundamental properties that, according to the math, should balance out perfectly in the grand cosmic equation. Charge flips positive to negative, parity mirrors spatial dimensions, and time reversal turns cause and effect backward. Individually, these symmetries sometimes break, but physicists believe the universe always obeys their combined balance. Here's the kicker. If you apply all three transformations at once, the equations suggest you'd get a valid, self-contained universe, one where atoms spin the opposite way, stars burn in reverse, and history unfolds from future to past. Antimatter offers a tantalizing clue. Every particle we know has an antimatter twin with opposite charge. Electrons have positrons, protons have antiprotons. When matter and antimatter meet, they annihilate in a flash of energy. But here's the mystery. The Big Bang should have created equal parts matter and antimatter. So where did all the antimatter go? Some theorists propose it didn't vanish, it became the building blocks of that mirrored cosmos, a universe where antimatter dominates and time runs in reverse. Imagine two cosmic twins born from the same explosive moment, evolving in perfect opposition. In our universe, a cup shatters on the floor. In the mirror universe, shards leap back into an unbroken cup. Supernovas there might implode into stars, while black holes spew out matter instead of swallowing it. Even consciousness could flow backward, with memories of the future guiding actions in the past. The implications are dizzying. If a mirror universe exists, could we ever detect it? Signals can't cross the divide. Light from their stars would move away from us in time, rendering it invisible. But some scientists speculate that gravitational waves, ripples in spacetime itself, might carry faint echoes of mirrored events. Others hunt for anomalies in cosmic rays, particles that might bear the fingerprints of a flipped reality. This isn't just a thought experiment, it challenges our deepest assumptions about causality and existence. If time can flow both ways, is the arrow of time just an illusion of our perspective? Are there versions of us out there living our lives in reverse, their choices shaping a past we've already forgotten? The mirror universe theory doesn't just ask what lies beyond our cosmos, it forces us to question which direction beyond even points. Imagine standing at a crossroads where every possible path doesn't just exist in theory, it becomes reality. That's the wild promise of the quantum many worlds interpretation, a theory that turns every tiny quantum decision into the birth of an entirely new universe. Unlike other multiverse ideas that imagine parallel worlds floating in some higher dimensional space, this one suggests that reality itself is constantly splitting, branching into infinite versions of itself with every quantum event. Every time an electron spins left instead of right, every time a particle could go here or there, the universe doesn't choose. It takes both paths, spawning two new realities where each outcome plays out. This idea grew from the bizarre puzzles of quantum mechanics, where particles exist in multiple states at once, a phenomenon called superposition. In the classic double-slit experiment, a single particle behaves like a wave, passing through both slits simultaneously until it's observed, collapsing into one definite position. The many worlds interpretation flips this on its head. There is no collapse. Instead, the observer themselves splits into multiple versions, each witnessing a different outcome in their own newly minted universe. One version of you sees the particle go left, another version, just as real, sees it go right. The implications for free will are staggering. If every possible quantum outcome manifests in some branch of reality, then every choice you've ever made or didn't make is playing out somewhere else. That morning coffee you skipped, there's a universe where you drank it, and another where you spilled it, and another where you invented a new flavor altogether. The branching isn't just limited to human decisions either. Stars explode differently in other branches, galaxies form alternate shapes, and even the laws of physics might subtly diverge over cosmic timescales. Critics argue this theory is untestable after all. We can't hop between branches to check, but proponents point to quantum computing as potential evidence. These machines harness superposition to perform calculations, and their strange efficiency might hint at parallel worlds working in tandem. Some even suggest that déjà vu could be fleeting moments where branches momentarily overlap, giving us whispers of lives we're living elsewhere. The many worlds interpretation doesn't just reshape our understanding of reality, it redefines you. There's a version of you reading this in a universe where gravity is weaker, where the Roman Empire never fell, or where your hair is blue. Infinite variations, all equally real, all sprouting from the quantum foam of possibility. It's a humbling thought. Every moment is a fork in the road, and every road is taken. What if the universe isn't just described by math? What if it is math? That's the radical proposition at the heart of the mathematical universe hypothesis, a theory championed by physicist Max Tegmark. Imagine peeling back the layers of reality, past atoms, past quantum fields, past space and time, until you're left with nothing but pure, abstract mathematical relationships. No matter, no energy, just equations. In this view, everything we perceive, the swirl of galaxies, the warmth of sunlight, even the flicker of consciousness, is just a shadow cast by deeper mathematical truths. Our universe wouldn't be a physical thing running on math. It would be the math itself, a structure as real and tangible to an outside observer as numbers on a page. Tegmark takes this even further. If our universe is fundamentally mathematical, then why stop at one? Every possible mathematical structure, every consistent set of equations, every logical framework could describe its own self-contained reality. Some might resemble ours with slight tweaks, like universes where prime numbers behave differently or geometric shapes have extra dimensions. Others could be so alien they defy visualization, realities built on mathematical constructs we haven't even discovered yet. Picture an infinite library where each book isn't just a story, but an entire cosmos defined by its own unique equations. This idea blurs the line between existence and abstraction. Take the number pi, for example. It's an infinite, patternless sequence that exists independently of any physical circles, a mathematical truth waiting to be uncovered. In Tegmark's framework, pi isn't just a tool we use. It's as real as the stars, and a universe where it governs spatial curvature would be equally real. Even more mind-bending is the implication that all computable structures must exist somewhere in the multiverse, a universe where 2 + 2 = 5. Impossible by our math, but Tegmark argues alternative mathematical frameworks could produce self-consistent realities where such rules hold true. Critics argue this stretches the definition of existence to the breaking point. If every mathematical structure is equally real, does that mean a universe described by a single equation, like x = 3, exists as fully as ours? Tegmark counters by distinguishing between simple and complex structures, suggesting conscious observers like us naturally find ourselves in rich mathematical environments capable of supporting complexity. It's a modern twist on the anthropic principle. We don't live in a special universe, just one mathematically elaborate enough to ask the question. Evidence for this theory might lie in the unreasonable effectiveness of mathematics itself. Why do equations like Einstein's relativity or quantum mechanics predict reality so precisely unless they're tapping into something fundamental? Some physicists hunt for universal mathematical patterns, constants, or symmetries that appear across seemingly disconnected phenomena, hinting at a deeper structure beneath the noise. Others suggest that if our universe is purely mathematical, there should be no uncomputable phenomena. Every physical law should be expressible in finite terms. Finding even one exception could unravel the hypothesis. The philosophical implications are staggering. If reality is mathematics, then discovery isn't invention, it's exploration. Every breakthrough, from Newton's gravity to quantum field theory, isn't just modeling the universe but decoding its true nature. It raises haunting questions. Are we the universe's way of understanding itself, or are we merely patterns in the data, fleeting configurations in an eternal mathematical landscape? Tegmark's vision doesn't just challenge what lies beyond our universe, it redefines what the universe is, turning the cosmos from a place into a proposition, written in the timeless language of numbers. What if the end of our universe isn't an ending at all, just the start of another? That's the breathtaking premise of conformal cyclic cosmology, a theory proposed by physicist Roger Penrose that rewrites cosmic history as an endless loop of rebirth. Imagine a universe that expands, cools, and fades into an eternity of darkness, only for that very emptiness to become the seed of the next Big Bang. This isn't science fiction. It's a daring mathematical vision where time itself resets and the cosmos is caught in an infinite dance of creation and dissolution. At the heart of Penrose's idea is something called conformal rescaling, a mathematical trick that lets you stretch or shrink the fabric of space-time without changing its essential shape. Picture an old photograph fading with age. The colors bleach away, the details blur, but the underlying composition remains. In this theory, as our universe approaches heat death, where all matter decays and even black holes evaporate, it doesn't vanish. Instead, it becomes indistinguishable from the high-energy, ultra-smooth state of a new Big Bang. The end of one cycle seamlessly transforms into the beginning of the next, like a phoenix rising from its own ashes. But how could we ever prove such a mind-bending idea? Penrose points to the cosmic microwave background, the afterglow of the Big Bang, as a potential celestial fossil. He claims to have found eerie, circular patterns in this ancient light, which he calls Hawking points. These faint, ring-shaped anomalies, some spanning billions of light years, could be the imprints of supermassive black holes from a previous cosmic cycle. According to the math, as black holes in one universe evaporate via Hawking radiation, their energy might leave ghostly signatures in the next cycle's CMB, like cosmic handprints pressed into the dawn of time. Critics argue these patterns could just be random fluctuations, but Penrose's team has statistically analyzed them, claiming the odds of such perfect concentric circles forming by chance are astronomically low. If confirmed, it would mean our universe isn't the first and won't be the last. Each cycle would carry faint echoes of its predecessors, like a message whispered across eternity. The implications are profound. Instead of a lonely, one-shot universe, we'd inhabit a link in an infinite chain, each iteration subtly shaped by the one before. Galaxies might form in similar patterns, physical constants could reset within narrow bounds, and the arrow of time itself might be part of a grander rhythm. Penrose's vision merges the poetic with the rigorous, suggesting that even in the coldest, darkest reaches of cosmic death, there's a spark waiting to ignite the next chapter. So the next time you hear about the heat death of the universe, remember, in this radical view, the end is just a prelude and the cosmos is a story with no final page, only endless new beginnings. If every possible universe you could dream up exists somewhere, then reality isn't just stranger than we imagine, it's stranger than we can imagine. Welcome to the ultimate ensemble theory, the most radical version of the multiverse where everything that can exist does exist. No limits, no constraints, just an infinite cosmic catalog of every conceivable reality, from universes with 17 dimensions to ones where gravity repels instead of attracts, or even realities where the rules of logic itself bend and twist. This isn't science fiction, it's the far edge of theoretical physics, a place where the word possible loses all meaning because nothing is left out. At its core, the ultimate ensemble theory takes the multiverse concept to its logical extreme. Most other theories like bubble universes or quantum branches still operate within some framework, whether it's inflationary cosmology or string theory. But here, there are no guardrails. If you can describe it mathematically, it exists. Picture a library where every book isn't just a variation on a theme, but an entirely different language written in symbols we've never seen. Some universes might have time that flows in loops or where cause and effect work backward. Others could be frozen, static worlds where change is impossible, or chaotic realms where the laws of physics shift like sand. One of the most unsettling implications, even universes that seem impossible to us might find a place in this ensemble. Take a reality where 2 + 2 = 5. In our logic, that's nonsense, but if the mathematical structure of that universe defines its own consistency, who's to say it couldn't exist? Or consider a cosmos where entropy decreases over time, making shattered glasses leap back onto tables and stars reassemble from cosmic dust. These aren't just thought experiments, they're potential realities in the ultimate ensemble, each one as valid as our own. The theory doesn't just stop at physics. It dives into metaphysics. Could there be universes where consciousness arises from entirely different substrates, not neurons, but swirling clouds of dark matter, or ripples in space-time itself? Might some realities be pure math with no physical substance at all, just abstract relationships humming in the void? The ultimate ensemble doesn't discriminate. If it can be coherently described, it's out there, somewhere in the vast, unending sprawl of existence. Critics argue this makes the theory untestable by definition. If everything exists, how could we ever find evidence? But proponents counter that it's the only framework that doesn't require fine-tuning. Our universe's constants, the strength of gravity, the mass of an electron, seem perfectly calibrated for life. The ensemble theory shrugs, of course they do. In an infinite multiverse, every combination gets its moment, and we just happen to live in one where the numbers let us ask the question. And here's the real kicker. the ultimate ensemble might be the only theory where the multiverse isn't generated by some mechanism like inflation or quantum branching. Instead, it simply is eternally and unconditionally. No beginnings, no endings, just an endless, static landscape of all possible realities, each one a self-contained island in the sea of existence. It's a vision so vast it dwarfs time and space, reducing even eternity to a footnote. So the next time you wonder, what if, remember somewhere in some corner of the ultimate ensemble that what if isn't a question. It's a universe playing by its own rules, waiting to be imagined. What if the universe isn't held together by gravity alone, but by invisible threads of electricity weaving through the cosmos? This is the plasma universe theory, a radical alternative to the Big Bang that paints reality as an infinite, electrified tapestry where stars, galaxies, and even the voids between them are connected by currents of ionized gas. Forget isolated islands of matter drifting in darkness here. The universe hums with electromagnetic energy, a dynamic network where filaments of plasma stretch across billions of light years, shaping everything we see. At the heart of this idea is plasma itself, the fourth state of matter, a sea of charged particles so dominant it makes up over 99% of the visible universe. From the fiery surface of the Sun to the glow of nebulae, plasma is everywhere. Proponents of this theory, like physicist Hans Alfvén, argue that magnetism and electric currents play a far greater role in cosmic evolution than gravity alone. They point to vast structures like galaxy clusters aligned along sweeping filaments, eerily reminiscent of lightning frozen in space. These aren't accidents, they argue, but evidence of massive electric circuits operating on scales we're only beginning to map. So how does this rewrite the story of beyond? In the plasma cosmos, there's no need for a singular Big Bang, no moment of creation from nothing. Instead, the universe could be eternal, with matter and energy endlessly recycling through cosmic circuits. Galaxies might form where these currents twist and knot, their spiral arms shaped by electromagnetic forces rather than gravity's slow pull. Even the mysterious voids between galaxies take on new meaning, not empty deserts, but regions where plasma currents have carved out pathways, like rivers etching valleys into bedrock. The implications are staggering. If the universe is fundamentally electric, then what lies beyond our observable horizon might not be more galaxies drifting apart, but an infinite continuation of this charged web, with structures and phenomena we can't yet imagine. Some theorists suggest that colossal plasma formations, far larger than anything we've seen, could exist out there, acting as cosmic generators powering entire swaths of reality. Others speculate that dark matter, the elusive substance thought to hold galaxies together, might not be a particle at all, but the gravitational shadow of these hidden currents. Critics point out gaps like the lack of a plasma-based explanation for the cosmic microwave background, the afterglow of the Big Bang. But plasma cosmologists counter with their own evidence. Lab experiments showing how electrified gas self-organizes into structures eerily like galaxies, or observations of intergalactic magnetic fields stronger than gravity alone can explain. The debate isn't just academic, it challenges whether we've been reading the universe's story with the wrong dictionary. Imagine a cosmos where lightning isn't just a weather phenomenon, but the architect of reality itself. Where the auroras dancing at Earth's poles are tiny echoes of forces shaping quasars and superclusters. The plasma universe theory doesn't just ask what lies beyond, it redefines beyond as something alive, crackling with energy, and infinitely older than we ever suspected. What if every moment of your life, every joy, every sorrow, every choice you've ever made is destined to replay in exactly the same way, over and over for eternity? This is the haunting premise of the time loop universe, a theory that twists cosmic history into an infinite Ouroboros, a snake forever devouring its own tail. Unlike cyclical models where each universe rebirths with variations, here the cosmos doesn't just repeat, it replicates down to the last atom, the last thought, the last breath. The universe collapses, rebounds, and unfolds again in perfect, unyielding symmetry. You've lived this life before, and you'll live it again an infinite number of times. The roots of this idea stretch back far beyond modern physics. Philosopher Friedrich Nietzsche called it eternal recurrence, a thought experiment so unsettling he believed it could either crush a person's spirit or forge them into something unbreakable. Imagine, he proposed, that a demon whispered to you, "This life as you now live it, you will have to live once more and innumerable times more." Would you despair? Or would you find meaning in the inevitability? Nietzsche's challenge wasn't just metaphysical, it was a litmus test for how deeply one could embrace existence. But what does science say? Enter conformal cyclic cosmology, a modern twist on the time loop penned by physicist Roger Penrose. His math suggests that as the universe approaches heat death, a state of maximum entropy where all energy is evenly spread, the distinction between empty and full vanishes. Time loses meaning, and in that featureless void, the end becomes indistinguishable from the Big Bang's fiery beginning. The cycle resets not just in structure but in perfect detail. Every galaxy, every planet, every life form reassembles precisely as before, like a cosmic phonograph needle lifting and dropping back onto the same groove. The eerie beauty of this model lies in its austerity. There's no multiverse, no branching paths, just one universe trapped in an endless rerun. Quantum fluctuations would play out identically each cycle, ensuring every electron, every photon takes the same path. Your first kiss, your greatest regret, the exact arrangement of stars on the night you were born, all locked in an unbreakable script. Even your awareness of this theory might be part of the loop, a recurring epiphany that flickers and fades with each iteration. Critics argue this violates the unpredictability of quantum mechanics, where particles behave probabilistically. But Penrose counters that quantum randomness might reset with each cycle, like a deck of cards reshuffled to the same order. Others hunt for anomalies, subtle imperfections in the cosmic microwave background that could betray previous cycles. If the universe truly loops, collisions between supermassive black holes in one era might leave faint, concentric ripples in the next, ghostly fingerprints of a time before time. The psychological weight of eternal recurrence is staggering. It's one thing to imagine parallel universes where choices diverge, but another to confront a reality where every mistake is fated, every triumph preordained. Yet there's a strange comfort here too. In a cosmos without true endings, nothing is ever lost. Every moment of beauty, every act of love echoes forever in the dark. The universe forgets nothing because it never really moves on. So the next time you watch a sunset, consider this. You've stood here before, beneath this exact sky, with these exact thoughts. And when the cosmos breathes its last and begins anew, you'll stand here again, not a copy, not an echo, but you in every particular, as if for the first time. The loop closes, the story starts again, and somewhere in the silence between cycles, the universe waits to tell it one more time. What if the universe isn't made of matter or energy at all, but of information? Imagine reality as a vast cosmic hard drive, where every particle, every force, even your thoughts are just data points in an unfathomably complex computation. This is the information universe theory, a mind-bending framework that suggests the fabric of existence might be built not from atoms, but from bits, the ones and zeros of an underlying code. In this view, the Big Bang wasn't an explosion of matter, it was the boot-up sequence of a cosmic program, and we're all just lines in its running script. The roots of this idea stretch back to quantum mechanics, where particles behave less like tiny billiard balls and more like flickering probabilities, mathematical abstractions until observed. Take the double-slit experiment. A single electron can act as both a particle and a wave, its behavior changing based on whether we're watching. This hints that reality might not be a fixed thing, but something that renders in real time, like a video game loading textures only when a player looks. Physicist John Archibald Wheeler captured this perfectly with his phrase, "it from bit." The notion that every particle, every field, even space-time itself derives from information. But how deep does this rabbit hole go? Digital physics takes it further, proposing that the universe isn't just described by information, it is information. Think of a Minecraft world. The blocks seem solid, but beneath the surface, they're just data structures governed by rules. Our universe could operate similarly, with Planck-scale pixels, tiny units of space-time forming the resolution of reality. Even gravity and quantum weirdness might emerge from how this cosmic processor handles data compression or error correction. The implications are staggering. If the universe is computational, then what's running the program? Some theorists, like MIT's Seth Lloyd, suggest it might not need an external programmer. The universe could be a self-contained, self-executing algorithm with the laws of physics as its operating system. Others speculate we're inside a simulation, a hypothesis that's gained traction with tech figures like Elon Musk. But here's the twist: even if we are, it doesn't make us any less real. In an informational universe, everything is code, including the coder. Evidence might lie in the universe's uncanny efficiency. Black holes, for instance, seem to store information on their surfaces, not their volumes, like a holographic projection. This aligns with the idea that reality is fundamentally 2D data painted onto a 3D canvas. Even quantum entanglement, spooky action at a distance, could be a feature, not a bug. Entangled particles might be linked by underlying data packets, instant updates in the cosmic network. So next time you scroll on your phone or stream a video, consider this. You might not just be using information. You might be at a fleeting pattern in the universe's grand computation, as ephemeral and essential as a single line of code in an infinite program. Picture a universe where every galaxy, every atom, even your own thoughts are nothing more than shimmering projections like shadows cast on the walls of an endless cosmic cave. Now take that idea and multiply it infinitely, where each universe is its own hologram, flickering into existence from an unseen boundary, and you've stumbled upon the holographic multiverse theory. It's a mind-melting fusion of two radical ideas. The holographic principle, which suggests our three-dimensional reality is a projection from a two-dimensional surface, and the multiverse, where countless universes coexist in a vast, interconnected web. But here's the twist: instead of separate bubbles floating in some higher dimensional space, each universe in this model is a self-contained hologram, encoded on its own distant boundary, all existing within a grand meta-reality we can't even begin to perceive. Think of it like a multiplex cinema where each screen shows a different film, a different universe with its own physics, its own history. But unlike a regular movie theater, these screens aren't just displaying light, they're generating reality itself. The images you see, the stars, the planets, the people aren't just illusions. They're the result of information etched onto the cosmic equivalent of a film reel, the two-dimensional edges of each universe. And just as a hologram can store a 3D image on a flat surface, these universes encode everything, every law of physics, every particle's position on their boundaries. The three-dimensional world we experience, just a side effect, a projection so convincing we'd never guess it's not the real thing. This idea didn't come out of nowhere. It builds on the work of physicists like Leonard Susskind and Gerard T. Hooft, who realized that black holes might hold the key to understanding holography. When matter falls into a black hole, its information isn't lost. It gets smeared across the event horizon, the point of no return. That means all the data describing that matter, from its temperature to its atomic structure, is stored on a 2D surface, just like the pixels on a screen. Now stretch that logic to the entire universe. If a black hole's interior can be described by information on its boundary, why not everything else? Some theorists argue that the cosmic microwave background, the afterglow of the Big Bang, could be that boundary for our universe, a spherical shell of data projecting the reality we know. But the holographic multiverse takes it further. If our universe is a hologram, why couldn't others be too? Imagine a higher dimensional, bulk space, not the 3 dimensions we're used to, but a realm with 4, 5, or even 11 dimensions, where each holographic universe floats like a soap bubble, its surface etched with the code for an entire cosmos. Some of these holograms might be nearly identical to ours, with slight tweaks. Maybe gravity is a fraction stronger, or time flows backward. Others could be unrecognizable, realities built on entirely different mathematical rules where concepts like space or causality don't even apply. And just like soap bubbles, these holograms could drift, collide, or even merge, their boundaries brushing against each other in ways that send shockwaves through their projected realities. The implications are staggering. If the holographic multiverse is real, then the search for other universes isn't just about peering into distant dimensions, it's about decoding the data on their edges. Some scientists speculate that if 2 holographic universes ever collided, the interference might leave scars in their cosmic microwave backgrounds, like glitches in a simulation. Others suggest that dark energy, the mysterious force accelerating the expansion of our universe, could be a side effect of our hologram's code updating, a cosmic buffer struggling to render an ever-growing reality. Even the laws of physics themselves might not be fundamental, just emergent properties of how information is processed on the boundary. So the next time you look up at the stars, consider this. Those distant points of light might not just be far away in space. They could be pixels in a projection, part of a universe-wide hologram sharing a higher dimensional stage with countless others. And beyond the edges of our cosmic screen, in the unfathomable bulk of the multiverse, who knows what other realities are flickering into existence, each one a self-contained illusion, each one as real as our own. Imagine the entire universe moving like a river, not just stars and galaxies drifting apart in the expansion, but entire clusters of them streaming in the same direction, as if pulled by some invisible current. This eerie cosmic motion is called dark flow, and it's one of the most baffling mysteries in modern cosmology. When astronomers mapped the movement of thousands of galaxy clusters, they found something impossible. These colossal structures, each containing hundreds or even thousands of galaxies, were all drifting toward a single point beyond the edge of what we can observe. It wasn't just random motion. The clusters were moving at speeds exceeding 2 million miles per hour, as if something massive out there was tugging on them. And whatever it is, it lies beyond our cosmic horizon, hidden from view. So what could possibly exert such a gravitational pull on the entire observable universe? The most unsettling possibility is that the dark flow is evidence of structures outside our universe, other cosmic domains in the greater multiverse, exerting their influence across the void. Picture a vast ocean with our universe as just one bubble floating in it. Nearby bubbles, other universes with their own physics, might be close enough to tug on ours, their gravity leaking through the fabric of space-time like ripples in water. Some theories suggest these neighboring realms could be unimaginably dense, packed with matter we've never encountered, or even infinite sheets of mass stretching through higher dimensions we can't perceive. The dark flow, then, would be the shadow of their presence, a ghostly fingerprint left on our cosmos. But there's another, even stranger explanation. What if the dark flow isn't caused by other universes at all, but by remnants of the pre-Big Bang cosmos? Some models suggest that before our universe existed, there was another, an earlier iteration that collapsed into a singularity before rebounding as our Big Bang. The gravitational imprint of that ancient universe might still linger, warping space-time in ways that distort the motion of everything we see. It's like finding ruins buried beneath a city. even though the old structures are gone, their foundations still shape the land above. If true, the dark flow could be the echo of a cosmos that died long before ours began. The implications are staggering. If the dark flow is real, and not some measurement error or cosmic illusion, it would mean our universe isn't just connected to something beyond, but fundamentally unbalanced, caught in a current we can't escape. Future observations, like those from next-generation telescopes probing the cosmic microwave background for subtle distortions, could either confirm this or send theorists back to the drawing board. Either way, the mystery lingers. What unseen force is steering the universe, and what does it reveal about the greater reality we're just beginning to glimpse? So the next time you hear about the expansion of the universe, remember, it's not just stretching outward. Somewhere out there, in the darkness beyond our sight, the cosmos might also be flowing, pulled toward something we may never fully understand. What if the Big Bang wasn't a fiery explosion from nothing, but the cosmic aftershock of two parallel worlds slamming together in a hidden dimension? This is the startling vision of the ekpyrotic universe model, a theory that rewrites the origin story of everything by replacing the singularity with a collision of titanic proportions. Picture two enormous flat membranes. Think of them as cosmic sheets floating in a higher dimensional space, separated by a gap tinier than an atom. These aren't just any sheets, they're entire universes or branes, each brimming with their own matter, energy, and physical laws. Then, in a cataclysmic instant, they crash together. The impact sends shockwaves rippling through both branes, igniting a firestorm of particles and radiation, what we now call the Big Bang. No singularity, no inexplicable moment of creation, just the violent meeting of two worlds we'll never see. The ekpyrotic model, rooted in string theory's brane cosmology, flips traditional inflation theory on its head. Instead of space expanding exponentially from a point, this scenario suggests our universe began as energy redistributed along a three-dimensional brane after a collision. The elegance lies in how it sidesteps inflation's thorniest puzzles, like why the universe appears so uniform. In standard cosmology, inflation stretches space so rapidly that distant regions lose contact, yet mysteriously share identical temperatures. But with ekpyrosis, those regions were once part of the same pre-collision brane, naturally explaining their symmetry. The model also smooths out cosmic wrinkles more efficiently than inflation, offering an alternative solution to why the universe isn't lumpy with uneven densities. Here's where it gets even wilder. The ekpyrotic model implies this wasn't a one-time event. These branes could oscillate, drifting apart, then gravitationally drawn back into another collision. Our universe's birth might just be one chapter in an endless cycle of cosmic near misses and crashes. Imagine two sheets of paper floating in a breeze, occasionally touching, each contact sparking a new universe. Some versions of the theory suggest the branes are locked in an eternal dance, colliding and separating like clockwork, producing big bangs at regular intervals. But how would we test such a radical idea? Evidence might lie in gravitational waves. While inflation predicts a particular spectrum of primordial ripples in space-time, ekpyrosis leaves a distinct signature, a sharper, more subdued pattern. Future observatories like the Laser Interferometer Space Antenna could detect these differences, potentially ruling one theory out. Another clue could lurk in the cosmic microwave background. If the branes were slightly misaligned during their collision, they might have created subtle swirls in the polarization of this ancient light, a fingerprint waiting to be found. Critics argue the model struggles to explain certain observed features, like the universe's slight unevenness at large scales. Yet supporters counter that ekpyrosis naturally incorporates dark energy, the mysterious force accelerating cosmic expansion, as the branes slowly drift apart post-collision. And then there's the philosophical appeal. A universe born from collision feels less like magic and more like mechanics, a cosmic accident we can almost touch with math. So the next time someone mentions the Big Bang, picture this alternative two shadow worlds, moving unseen in dimensions beyond our own, their violent embrace lighting the spark of everything we know. It's a reminder that the universe's origins might be stranger and more beautiful than we ever imagined. Now imagine peeling back the layers of reality until you reach a point where even space and time dissolve, not just an empty void, but the complete and total absence of everything. No particles, no fields, no dimensions, not even the faintest whisper of potential. This is the null universe hypothesis, the most extreme vision of what might lie beyond our cosmic horizon, pure, unfiltered nothingness. Not darkness, because darkness requires space to exist. Not emptiness, because emptiness implies a container. This is the absolute negation of existence itself, a state so alien to our experience that even the word nothing feels inadequate to describe it. The idea isn't just a flight of philosophical fancy, it emerges from the razor's edge of cosmology and quantum theory. Quantum mechanics tells us that even a perfect vacuum isn't truly empty. It seethes with virtual particles flickering in and out of existence, a quantum foam of potential. But what if, beyond the boundaries of our universe, that foam settles into absolute stillness? No fluctuations, no energy, no space-time fabric to ripple. Just nothing. Some models of the Big Bang's aftermath suggest that inflation, the rapid expansion of space, might have left behind regions where the process stalled, creating pockets of true vacuum where the laws of physics simply don't apply. These null zones wouldn't be places, they'd be the total absence of place, like holes in the canvas of reality. The philosophical weight of this idea is crushing. Human thought is built on relationships, objects in space, events in time, but true nothingness has no reference points, no there to anchor meaning. Ancient philosophers like Parmenides argued that nothingness couldn't exist because speaking of it implies it's something, a paradox that still haunts modern physics. Even mathematics struggles with absolute zero, divide by nothing, and the system breaks. Yet the null hypothesis forces us to confront this paradox head-on. If our universe is finite, what lies outside it? If the answer is nothing, does that nothingness exert influence, like a cosmic pressure keeping our universe contained? Some theorists propose that the null state isn't passive but active, a sort of existential ground zero that constantly presses against existence, shaping its boundaries. Think of a bubble floating in a void. The surface tension holding it together isn't just internal, it's the absence outside pulling equally hard. If true, this could explain why our universe isn't infinite, or why dark energy's repulsive force seems fine-tuned to prevent total dispersal. Even more unsettling is the possibility that null regions might not be static. Could true nothingness expand, eroding the edges of reality like a cosmic tide dissolving sandcastles? The implications ripple through theology, metaphysics, and even the nature of consciousness. If awareness requires a substrate, neurons, quantum vibrations, anything, then a null universe would be the only state where thought is truly impossible. No observers, no measurements, no collapse of quantum probabilities. It's the ultimate silence beyond even the concept of silence, and yet, in this total negation, some find a strange solace. If the null hypothesis is correct, then our universe isn't just rare. It's a defiance, a spark against the void. Every galaxy, every atom, every fleeting thought becomes a rebellion against nothingness, a temporary victory in an endless war with oblivion. So the next time you gaze at the night sky, consider the abyss beyond the last visible star. Not the darkness, not the empty space, but the sheer, unthinkable nothing that might stretch forever. It's the only frontier we'll never cross, the only mystery we'll never solve, because to enter it would be to cease existing at all. What if the cosmos isn't just a cold, mechanical expanse, but a living, breathing ecosystem where universes are born, evolve, and even compete for survival? This is the radical beauty of the living universe theory, a vision that treats reality not as a static stage but as a dynamic, almost biological network where the laws of physics themselves might be subject to change, adaptation, and even cosmic Darwinism. At the heart of this idea is physicist Lee Smolin's groundbreaking proposal that black holes aren't just cosmic dead ends, but the reproductive organs of the universe, each one a seed for a new reality with slightly tweaked physical constants. Picture a vast cosmic forest where every black hole is a tree dropping acorns, each acorn sprouting into a new universe with its own unique blueprint. Smolin's theory, called cosmic natural selection, flips the script on how we think about the universe's fine-tuning. Why do the fundamental constants, the strength of gravity, the mass of an electron, seem perfectly calibrated for life? In this model, it's no accident. Universes that produce more black holes reproduce more often, passing their traits down to offspring universes. Over countless generations, universes with physics conducive to black hole formation like ours would dominate the cosmic landscape. Stars must live long enough to form heavy elements, collapse into black holes, and birth new universes. Too weak a gravity, stars might not collapse. Too strong, they could burn out before forming planets. The numbers we observe aren't arbitrary, they're the result of eons of cosmic trial and error. But how would this even work? Imagine a black hole's singularity not as a dead stop, but as a cosmic reset button. As matter crushes down to infinite density, the extreme conditions could trigger a new Big Bang, but with a twist. The fundamental constants might shift slightly, like genetic mutations in biology. Some offspring universes would be sterile, no black holes, no further reproduction. Others might be black hole factories, spreading their physics far and wide. Over time, the multiverse would become dominated by universes fine-tuned for black hole production, much like Earth is dominated by organisms fine-tuned for survival. The implications are staggering. If true, our universe isn't just one iteration, it's the latest in an ancient lineage, shaped by the same forces that drive evolution on Earth. Even the arrow of time might be a product of this selection. Universes where entropy increases consistently could simply outcompete those where time behaves chaotically. Critics argue there's no way to test such a theory after all. We can't observe other universes or their black hole offspring. But Smolin suggests potential signatures. Universes optimized for black holes might produce them at a predictable rate or exhibit certain statistical patterns in their distribution. Future telescopes mapping the cosmos in unprecedented detail could hunt for these subtle clues. This theory doesn't just reshape our understanding of reality, it redefines our place in it. We're not just inhabitants of a universe, we're part of a living, breathing cosmic lineage, our very existence a testament to generations of universes that came before, each one fine-tuning the rules until life could emerge and ask the question, where did we come from? The answer might be written not in equations alone, but in the relentless, beautiful logic of cosmic survival. What if the universe isn't just observed by consciousness, but built from it? This is the spine-tingling premise of the consciousness-created universe theory, a radical idea that flips traditional physics on its head. Instead of matter and energy forming the bedrock of reality, this perspective suggests consciousness itself might be the fundamental fabric, weaving existence into being with every thought, observation, and measurement. At the quantum level, particles exist in a haze of probabilities until observed, a phenomenon that's baffled scientists for decades. But what if that's not a quirk of physics, but a clue? What if the act of observation doesn't just reveal reality, it creates it? This isn't just philosophical musing. Quantum mechanics has long wrestled with the measurement problem. In experiments like the double slit, particles behave as waves when unobserved, fanning out into multiple possibilities. But the moment a detector clicks on, they snap into a single, definite state. The textbook explanation calls this wave function collapse, but the deeper question remains, what triggers it? Some theorists, like Nobel laureate Eugene Wigner, propose that consciousness itself might be the catalyst, that the universe remains a blur of probabilities until a conscious mind pins it down. It's as if reality is a cosmic choose-your-own-adventure book, with each conscious observer turning the page. Now imagine stretching this idea beyond our universe. If consciousness shapes reality here, could other universes have entirely different conscious foundations? In a hypothetical realm where consciousness operates collectively like a hive mind, quantum events might resolve differently, with particles behaving in ways we'd find bizarre. Or picture a universe where consciousness is tethered to structures we'd consider inanimate: rocks, stars, even space-time itself, birthing a reality where observation happens constantly on a cosmic scale. The laws of physics in such a place wouldn't just be written in math, but in the very act of perception. The implications ripple into metaphysics and beyond. If consciousness creates reality, does that mean the universe wants to be observed? Some interpretations of quantum biology suggest that even primitive life forms, bacteria, plants, might play a role in collapsing quantum states, subtly shaping their environment. Others speculate that advanced civilizations could harness this principle, engineering realities through sheer intentionality. And then there's the eerie possibility that in universes without observers, reality remains forever fuzzy, a soup of unrealized potentials. Critics argue this veers into mysticism, but proponents point to cutting-edge research. Integrated information theory, for instance, attempts to quantify consciousness as a measurable property of complex systems, not just brains, but maybe even the universe itself. Experiments in quantum cognition explore how human decision-making might exploit quantum processes, blurring the line between mind and matter. Even the hard problem of consciousness, why subjective experience exists at all, takes on new urgency if experience is foundational, not emergent. So the next time you watch a sunset or marvel at the stars, consider this. You might not just be witnessing the universe, but participating in its creation. And somewhere beyond our cosmic horizon, other realities could be unfolding under entirely different rules, not of particles or forces, but of perception itself. The ultimate frontier might not lie in distant galaxies, but in the very nature of awareness, shaping worlds with every thought. Imagine zooming into the jagged edge of a snowflake. No matter how deep you go, the same intricate patterns repeat, spiraling endlessly into infinity. Now take that same principle and stretch it across the cosmos, and you've arrived at the fractal universe theory. This mind-bending idea proposes that the structure of our universe isn't just random or uniform, but infinitely self-repeating, like a cosmic hall of mirrors where galaxies, clusters, and superclusters organize themselves into patterns that echo across scales we can't even fathom. What we perceive as the edge of the observable universe might just be one tiny stitch in an unfathomably vast tapestry, woven with the same recurring motifs over and over again. The roots of this theory dig deep into mathematics. Fractals, shapes that repeat their geometry at every scale, are everywhere in nature, from branching rivers to the veins in a leaf. But when cosmologists apply this to the universe's large-scale structure, things get wild. Studies of galaxy distributions reveal something uncanny. Matter isn't scattered randomly. Instead, it clumps into filaments and voids, forming a cosmic web that looks eerily similar whether you're mapping a region 1,000,000 light-years wide or 1,000,000,000. This hierarchical clustering suggests the universe might not have a true scale, just layers upon layers of repeating complexity, like a Russian nesting doll where each doll is a universe unto itself. What would this mean for the nature of reality? If the fractal pattern holds beyond our cosmic horizon, the implications are staggering. Our entire observable universe, with its hundreds of billions of galaxies, could be a single node in a far grander structure. Zoom out far enough, and you might find that our universe is just one branch on an infinite cosmic tree, with other universes branching off in similar but subtly different configurations. Each of those universes would contain its own observable universes, and so on ad infinitum. There'd be no center, no edge, just an endless cascade of self-similarity, stretching forever in all directions. Some models take this even further. If the fractal nature is perfect down to the smallest scales, then even the atoms in your body might mirror the structure of galaxy clusters, with electrons orbiting nuclei like stars around a galactic core. It's a poetic idea that the universe isn't just in us, but we are miniature universes ourselves, each particle a reflection of the whole. Others argue the fractality might break down at certain scales, revealing deeper layers of order or perhaps something entirely unexpected. Critics point out that current observations only show fractality up to a point the cosmic web seems to smooth out at the very largest scales. But supporters counter that we're limited by what we can see. Beyond our observational horizon, the pattern could reassert itself in ways we'll never detect. The fractal hypothesis also challenges traditional cosmology's assumption of homogeneity, the idea that on large enough scales, the universe looks the same everywhere. If true, it would force us to rewrite textbooks on cosmic evolution, dark matter, even the Big Bang itself. So the next time you gaze at a spiral galaxy, consider this. You might be looking at a tiny fragment of a design so vast, so recursive that it defies comprehension. The universe could be less like a singular explosion and more like an infinite mosaic, every piece a reflection of the whole, a cosmic fingerprint where every wall contains another universe and every line tells the same ancient story. We've ventured through theories that stretch the imagination, parallel worlds, cosmic bubbles, even reality as a simulation. But what if the truth behind our universe's edges is something far more unsettling, that whatever lies beyond isn't just unknown but unknowable? Not because the answers are hidden, but because the human mind itself is fundamentally unequipped to comprehend them. Think of it like an ant trying to grasp quantum physics. No matter how intelligent the ant, the concepts exist on a scale its brain simply can't access. Our cognitive machinery evolved to navigate a three-dimensional world of medium-sized objects moving at moderate speeds. Reality's ultimate nature might operate on levels so alien, so abstract, that our very perception filters it out like static. Consider the humble neutrino. Trillions pass through your body every second, yet you'll never feel them because they barely interact with matter. Now imagine entire dimensions or forces equally imperceptible, not because they're rare, but because our senses and tools are tuned to a narrow slice of existence. Even our most advanced physics relies on metaphors, particles as tiny balls, space-time as a fabric, because raw mathematical truths defy visualization. String theory's extra dimensions, dark energy's repulsive force, these aren't just hard to picture, they resist any familiar analogy. Now scale that up to whatever exists beyond our cosmic horizon. If the universe is already this bizarre within observable limits, what incomprehensible structures might lurk further out? Philosophers call this the cognitive closure hypothesis, the idea that some truths sit forever beyond the reach of human understanding, not due to lack of effort, but because our brains lack the necessary hardware. Even consciousness itself might be a limiting factor. Just as a bat experiences sonar echoes in ways we can't subjectively replicate, a hyperdimensional entity might perceive realities that our minds automatically simplify or discard. Some theories suggest the ultimate nature of existence could be like a four-dimensional object projected into our three-dimensional perception. We only ever see fragmented shadows, never the whole. This humbling perspective doesn't mean we should stop searching. After all, science has repeatedly shattered previous limits of comprehension. Quantum mechanics and relativity once seemed inconceivable too. But it does invite a profound shift in how we frame the mystery. The cosmos may not withhold its secrets out of spite. It might simply be speaking a language we lack the organs to hear. Every generation believes it's on the verge of unlocking everything, only to find the universe's next layer even stranger. Perhaps the greatest discovery wouldn't be an answer at all, but the realization that some questions transcend the tools we have to ask them. So while we marvel at the theories, the multiverses, holograms, and cosmic loops, we're left with one haunting possibility: that the true face of reality might forever hover just beyond the edges of thought, visible only in the distortions it casts on the walls of our intellectual cave. From the infinite branching of the quantum multiverse to the haunting silence of the null universe, each theory we've explored cracks open a new window into reality's deepest mysteries. The holographic principle suggests we're living in a cosmic projection, while eternal inflation paints a picture of universe after universe bubbling into existence like foam on an endless sea. The living universe theory dares to imagine cosmos evolving like species, and the simulation hypothesis forces us to question whether the stars above are pixels in some grand design. What makes these ideas so compelling isn't just their audacity, it's how they reshape our understanding of existence itself. Take the fractal universe, where patterns repeat from the quantum scale to galactic superclusters, hinting at a reality far more interconnected than we ever imagined. Or consider the mirror universe theory, where antimatter dominates and time flows backward, a cosmic funhouse reflection that could explain why our universe seems to favor matter. Then there's cyclic cosmology, where the Big Bang isn't a beginning but a rebirth, each cycle leaving faint echoes in the fabric of space-time. These aren't just abstract thought experiments, they're lenses that transform how we see everything from black holes to the night sky. What's truly remarkable is how these theories complement and clash with one another. The brane world scenario and ekpyrotic model both rely on hidden dimensions, but one envisions cosmic collisions while the other imagines floating membranes. The mathematical universe hypothesis strips reality down to pure equations, while the consciousness-created universe theory places perception at the center of everything. Some ideas, like dark flow's unexplained cosmic current, leave us with more questions than answers, teasing the possibility of structures beyond our horizon that defy all current frameworks. Yet beneath their differences, all these theories share a common thread. They push the boundaries of human curiosity. Whether it's black holes birthing new universes or the unsettling notion that we might be lines in some cosmic code, they remind us that the universe is far stranger, far grander than our everyday experience suggests. This isn't just about solving puzzles, it's about expanding what we consider possible, about daring to look beyond the edge of the known and sitting with the wonder of the unknown. So which theory speaks to you? Does the elegance of the holographic universe resonate, or does the pulse of the living cosmos feel more alive? Maybe you're drawn to the stark simplicity of the null hypothesis or the infinite possibilities of the ultimate ensemble. Whatever you're leaning, one thing's certain: the universe is richer, more mysterious, and more astonishing than we've yet grasped. Keep questioning, keep marveling, and above all, stay hungry for the next great revelation waiting just beyond the stars. The greatest discoveries lie not in the answers we've found, but in the mysteries still shimmering just out of reach.